In this video, we're going to talk about optimization problems. The goal with these types of problems is that you're trying to optimize something. That is, you're trying to find the dimensions that will maximize the area of a plot of land, or that will minimize the amount of fencing required. Or if you're dealing with business type problems, you're trying to find a situation where you can achieve maximum profit or minimize costs. And so that's the goal of these type of problems. We're trying to find the optimal conditions to get the best results. So therefore, in order to solve these type of problems, you need to be able to identify the maximum and the minimum values of a function. So here we have a local maximum, and here we have a minimum. Now there's one important characteristic of these points in the graph. At the maximum value and at the minimum value, the slope of the horizontal tangent line is 0. Therefore, to find the location of a maximum or a minimum, what you need to do is you need to take the first derivative of the function, set it equal to 0, and solve for x. And you're going to see this in action as we work on problems. So let's go ahead and do that. Let's start with this one. Find two numbers whose sum is 60 and whose product is a maximum. So let's put some variables to these two numbers. Let's say that these two numbers are x and y. Now we have two variables. In order to solve for two variables, we need two equations. The two equations are going to be the sum and the product. So what's the sum of x and y? The sum of x and y is simply s is equal to x plus y. The product is just what it is. It's the multiplication of those two numbers, x times y. So those are the two equations that we have. Now here's a question for you. Which of these two equations would you say is the constraint equation, and which one is the objective function? The constraint equation is equal to a number, a fixed value. The objective function, it can vary. That's what we're trying to maximize or minimize. The objective function is the function that we're going to find the first derivative of, set it equal to 0, and solve for either x or y. Now we don't know the value of the product, but we do know the value of the sum. So the sum is a fixed value. Therefore, this is the constraint equation. And this is the objective function. What we need to do is we need to differentiate p. We need to find the first derivative of p, set it equal to 0, and solve for x or y. But right now we can't do that because p is in terms of two variables. We need to get p in terms of one variable before we can find the first derivative. And that's where the constraint equation comes. So what we're going to do is we're going to isolate y in the constraint equation. So let's subtract both sides by x. 60 minus x is equal to y. And then what we're going to do is in the objective function, we're going to replace y with 60 minus x. So we have p is equal to x times 60 minus x. Now let's go ahead and distribute x. So we have 60x and then minus x squared. So now we have p in terms of one variable. At this point, we could find the first derivative of p and set it equal to 0. So p prime is going to be 60 minus 2x. And let's set that equal to 0. So adding 2x to both sides, we get 60 is equal to 2x. And then dividing both sides by 2. We can see that x is 60 over 2, which is 30. Now at this point, we can go ahead and calculate y. So let's take 30 and let's plug it into this equation to get y. 60 minus 30 is equal to y. So y2 is 30 as well. So now we have both numbers whose sum is 60. If we wish, we can calculate the product by plugging it into this equation. So 30 times 30. We know that 3 times 3 is 9, and then if we add the two zeros, we get a product of 900. So that is the maximum product. So that's it for this problem. The two numbers are 30 and 30, and the maximum product is 900. Now let's make sense of these numbers. Let's check to see if we have the right answer. So what we're going to do is we're going to make a table. We're going to have x, y, the sum s, and the product p. The maximum product occurs when both x and y are 30. We get a maximum product of 900. What if x was 10 and y was 50? In this case, the sum is still 60, which that always has to be the case. 10 times 50 is 500, so this is not more than 900. If x was 20, y would have to be 40. The sum would still be 60, but 20 times 40 is 800. Now let's say if y was 23, x would have to be 37. 37 times 23 is 851. It's still less than 900. Let's say if x was 32 and y was 28. The sum is still 60. 32 times 28 is 896. Or if x is 29 and y is 31, 29 times 31 is 899. So regardless of what combination of x and y that we choose, as long as the sum of x and y is 60, the maximum product that we can achieve is 900. Any other combination of x and y with a sum of 60 will be less than 900. So we indeed have the right values of x and y that lead to the maximum product. And that's the goal of optimization. You want to find the numbers or the conditions that will maximize or minimize something. Number 2, find two numbers whose difference is 40 and whose product is a minimum. And also find the value of the minimum product. So let's write the equations. The difference of two numbers, let's say the two numbers are x and y. So let's say y is larger in value. So the difference is going to be y minus x. The product, just like before, is going to be x times y. Now, which will be the constraint equation and which one will be the objective function? We know the value of the difference. We don't know the value of the product. So because we know the value of the difference, this here, 40 equals y minus x, that's going to be the constraint equation. This is going to be the objective function. The objective is to minimize the product. So let's get this equation in terms of one variable. Let's add x to both sides. So we get 40 plus x is equal to y. Now let's replace y with 40 plus x in the objective function. So the product is going to be x times 40 plus x. And now let's distribute. So here we have x times 40, which is 40x, and then x times x, which is x squared. Now, let's find the first derivative of the objective function. That's going to be 40 plus 2x, and then let's set it equal to 0. Now I'm going to move the 2x to the other side, where it's going to be negative 2x, and then I'm going to divide both sides by negative 2. And so x is negative 20. So now that we know the value of x, we could plug it into the constraint equation to get y. So 40 plus negative 20 will give us y. And so that's equal to positive 20. So at this point, we have two numbers whose difference is 40. 20 minus negative 20 is positive 40. And now we need to calculate the product. So it's going to be negative 20 times 20. And so the product is going to be negative 400. So this is the minimum product that we can get from two numbers whose difference is 40. And let's confirm this with a table. So we're going to have x y, the difference d, and then the product p. So we had 20 for y and negative 20 for x. That gave us a difference of 40, but a product of negative 400. Let's see if we could find two other values for x and y with a difference of 40, but a product that's lower than negative 400. If we were to try 0 and 40, the difference will be 40, but the product 0 times 40 is 0. 0 is higher in value than negative 400, at least on a number line. So 0 is not the minimum product. If we try a value of 20 for x, y is going to be 40 units higher than x. So it's going to be 60, so that the difference is still 40. 20 times 60 is 1200. This is not less than negative 400, it's higher. We want to find something that's lower than negative 400. If we try 10 and 50, that's not going to work. This is going to be 500. If we were to try, let's say, negative 10 and 30, 30 minus negative 10, that's still positive 40, but this will be negative 300, which is still higher than negative 400. If we were to try negative 25 with 15, the difference is 40, but negative 25 times 15, that's negative 375. If we were to try negative 21 and 19, we would get negative 399. So the lowest product is negative 400. That is the minimum product that we can get with two numbers that have a difference of 40. And so we can see that the process works. So the answer is negative 20 and 20 with a minimum product of negative 400. Number 3, find two positive numbers whose product is 400 and whose sum is a minimum. Feel free to pause the video if you want to work on this. So the product is going to be x times y, and the sum is going to be x plus y. Now we're trying to minimize the sum, so the sum is the objective function. We have the value of the product, so the constraint equation will be 400 is equal to x times y. Once you replace p with 400, this becomes an equation. And so that right there is the constraint equation. Now let's solve for y. So let's divide both sides by x. So we get that y is 400 over x. Now let's replace y with that. So the sum is going to be x plus 400 over x. So now that we have our objective function in terms of one variable, we can go ahead and find the first derivative. But before we do that, let's rewrite this equation. Let's move the x variable to the top. So this is x plus 400 times x to the minus 1. Now let's find the s prime, the first derivative. This is going to be 1 minus 400, and then x, we'll subtract this by negative 1, so this becomes negative 2. And we'll set this equal to 0. Now I'm going to move this value to the other side, so it becomes positive. So we have 1 is equal to 400 times x to the minus 2. Now we can put this over 1, and let's bring the x back to the bottom so that the negative exponent will become positive. So this becomes 400 over x squared. Now let's cross multiply. 1 times 400 is 400, and 1 times x squared is x squared. If we take the square root of both sides, we get that x is going to be plus or minus 20. Now we want two positive numbers, so we're going to go with positive 20 instead of negative 20. So that's the value of x that we have so far. Now let's calculate the value of y. So let's plug it into this equation. 400 divided by 20 is going to be 20. You can cancel a 0. It becomes 40 over 2, which is 20. So we have the two numbers at this point. X is 20 and y is 20. Now the last thing we could do, which is optional, we don't have to, but we can calculate the sum. The minimum sum is going to be 20 plus 20, which is 40. And you can confirm this with a table, kind of like what we did before. But you'll find that the minimum sum, the lowest sum that we can get with two numbers that multiply to 400, is 40. Number 4. Find a positive number where the sum of that number and its reciprocal is a minimum. So let's use S for sum. Let's say the positive number is x. The reciprocal is 1 over x. Now this problem is a little bit different than the other problems we've considered so far because we don't have a constraint equation. All we have is the objective function. And that's okay because the objective function is not in terms of two variables. It's only in terms of one variable. So we can go ahead and find the first derivative. But before we do that, let's rewrite it as x plus x to the negative 1. Let's move this to the top. So now let's find the first derivative of s. The derivative of x is 1. The derivative of x to the minus 1 is going to be, we need to move the negative 1 to the front. And then we got to subtract the exponent by 1, which makes this negative 2. And we'll set that equal to 0. Now let's move this to the other side. So we have 1 is equal to 1x to the negative 2. Now let's bring this to the bottom. So we have 1 is equal to 1 over x squared. And then we can cross multiply. So this gives us 1 is equal to x squared. Taking the square root of both sides, x is equal to plus or minus 1. But we only want the positive numbers, so we're going to go with positive 1. So that's the answer for this problem. Now let's check our answer. So let's make a table where we're going to have x, 1 over x, and the sum. So when x is 1, 1 over x will be 1. The sum of x and the reciprocal, 1 plus 1 will be 2. Now, can we find some other positive number x where the sum and its reciprocal will be less than 2? Remember, we want to minimize the sum. If we were to make x equal to 2, this will be 1 over 2. 2 plus a half is 2.5. That's greater than 2, not less than it, so that doesn't work. If x is 3, this will be 1 over 3. This will be about 3.33. So let's pick a number lower than 2, but greater than 1. Let's say if we chose 1.5. 1 over x, or 1 over 1.5, that's 0.6 repeating. And if you add that to 1.5, you're going to get 2.16 repeating, which is more than 2. If we were to try 1.1, 1 over 1.1 is 0.90 repeating. So that's like 0.9090. And if you add that to 1.1, that will be 2.009, which is more than 2. If we try a number like 0.8, 1 over 0.8 is 1.25. And if you add that to 0.8, you get 2.05. So as we can see, the minimum sum is going to be 2. We can't get anything lower than that. And that occurs when x and its reciprocal, they're both equal to 1. Find the dimensions of a rectangle with a perimeter of 200 feet with an area as large as possible. So let's draw a rectangle. Now let's say this is the length and this is the width. The perimeter of a rectangle is 2L plus 2W. And we have the perimeter, so the perimeter is 200. Now to simplify this equation, I'm going to divide everything by 2. So this is going to be my constraint. 100 is equal to L plus W. The objective function is to maximize the area. We want the area to be as large as possible. And the area of a rectangle is length times width. Now let's solve for W in this equation. So we need to subtract both sides by L. 100 minus L is W. And now let's replace W in the objective function with 100 minus L. So we have the area is L times W, where W is 100 minus L. Now let's distribute L. So it's 100L minus L squared. So now, since we have the area, the objective function, in terms of one variable only, we can now find the first derivative. The derivative of 100L is 100, and the derivative of L squared is 2L. So let's set it equal to 0. Let's move negative 2L to the other side, so it can become positive 2L. And then we could divide by 2. So half of 100 is 50. So L is 50. So now we could use this equation to calculate W. So W is 100 minus L, so that's 100 minus 50, which is 50. So both the length of the rectangle and the width are equal to 50. Now, if we want to calculate the area, we could simply do length times width. And so the maximum area is going to be 50 times 50. And the units is going to be in feet. So 50 feet times 50 feet, that's 2,500 square feet. So that's the maximum area for this particular problem. And these are the dimensions. It's 50 by 50. A farmer has 600 feet of fencing and wants to create a rectangular field along a river. He needs no fence along the river itself. What are the dimensions of the field that has the largest area? So let's begin by drawing the river. So here we have the river, and he's going to create a fence around this river. So there's no need to put a fence here. Now, let's label the dimensions. So let's use X and Y. So let's call this Y, and let's call this X. So the perimeter is going to be X plus 2Y instead of 2X plus 2Y because there's no X here. So the perimeter is just the sum of all three sides. So it's X, and then Y plus Y gives us 2Y. Now we have the perimeter. The farmer has 600 feet of fencing. Remember, square feet is for area, and just feet is perimeter. So P is 600, and so this is the constraint. Now, he wants to maximize the area. He wants the largest area. And the area of a rectangle is length times width, or in this case, X times Y. So this is the objective function, and this is the constraint. For the constraint equation, should we solve for X or Y? I think it's easier if we solve for X, because if we solve for Y, we have to divide by 2. And you're going to have X over 2, and you have to deal with fractions. So let's subtract both sides by 2Y, or just move it to this side. So we have 600 minus 2Y is equal to X. No fractions. So now let's replace x in the objective function with 600 minus 2y. So the area is going to be 600 minus 2y times y. So let's distribute y. So it's going to be 600y minus 2y squared. So now that we have the area function or the objective function in terms of one variable, we should now find the first derivative. So it's going to be 600 minus 2 times 2y, which is going to be 4y, and then set it equal to 0. Now let's move the negative 4y to the other side. So it can become positive 4y. And then let's divide both sides by 4. So 600 divided by 4 is 150. So we now have the value for y. Now keep in mind x, we said it was 600 minus 2y. So that's going to be 600 minus 2 times 150. 2 times 150 is 300. And 600 minus 300 is 300. So we now have the dimensions. Y is 150 feet. X is 300 feet. Now to calculate the maximum area using this equation, it's going to be x times y, 300 feet times 150 feet. And let's see what that's going to be. So that's going to be 45,000 square feet. So that is the maximum area. So the dimensions are 300 feet by 150 feet with a maximum area of 45,000 square feet. So that's it for this problem. Now let's move on to the next problem. It's similar to the first but a little different. So we have this farmer. He wishes to create a rectangular field along a river, but this time he has a fixed area instead of a fixed perimeter, and the area has to be 10,000 square feet. What are the dimensions of the field that will require the least amount of fencing? And let's also determine the amount of fencing that he needs as well. So let's begin by drawing the river. And we have the same type of picture. So we're going to call this x and y. And you could try this problem if you want to as well. So this time the area is the constraint. So we know the area is x times y, and the area is 10,000 square feet. Now the perimeter is the stuff that we're trying to minimize because we want the least amount of fencing, and so that's going to be x plus 2y. Now I'm going to solve for y in this equation, so I need to divide by x. So y is going to be 10,000 divided by x. So now I'm going to replace y with that. So 10,000 times 2, that's 20,000. So the perimeter is going to be x plus 20,000 and then x to the negative 1. So now let's find the first derivative. That's going to be 1 plus 20,000 times negative 1 x to the minus 2. And then let's rewrite the expression. So we have 1 minus 20,000 over x squared. And let's set that equal to 0. So I don't need this picture anymore. But let's keep in mind that p is x plus 2y. So I'm going to take this term, move it to this side. So I have 1 is equal to 20,000 over x squared. And I'm going to write 1 as 1 over 1 and then cross multiply. So 20,000 is equal to x squared. Now, let's take the square root of both sides. So this will give us the value for x. So x, if you round it, it's going to be about 141.42 feet. So now that we have x, let's go ahead and calculate y using this equation. So y is going to be 10,000 divided by x, or divided by 141.42. So that's going to be about 70.7 feet. So that's the value for y. So now that we have x and y, which is what we needed to find, so that represents the dimensions of the rectangle, we can now calculate the minimum perimeter, or the minimum amount of fencing that we need. So it's going to be x plus 2 times y. So the perimeter is going to be approximately 282.8 feet. And that's the answer. Number 8. A farmer uses 1,600 feet of fencing to enclose a rectangular area which will be divided into 3 pens. What is the maximum total area of the 3 pens that he can enclose with the limited amount of fencing that he has available? Well, let's draw a picture. So we're dealing with a rectangle, and this rectangle is going to be divided into 3 pens. Now we could call the vertical lengths y and the horizontal length, or the horizontal fencing, x. So that's the situation that we have so far. Our goal is to maximize the area. The area of all 3 pens is simply x times y. It's length times width. Now the total amount of fencing is going to be the length of all of the sides. So we have x plus x, that's 2x, and then we have 4 y's that we need to add together. So that's going to be plus 4y. Now we can replace f with 1,600. So this is our constraint equation. Now all of the coefficients are even. So to simplify this equation, I recommend dividing everything by 2. So we get 800 is equal to x plus 2y. Now it's going to be a lot easier if we isolate x rather than y. So let's subtract both sides by 2y. So we get that 800 minus 2y is equal to x. Now let's plug this into our objective equation. And so we're going to replace x with what we have here, 800 minus 2y. So the area is going to be 800 minus 2y times y. So we got the area function in terms of one variable. Now let's distribute y. So this is going to be 800y and then minus 2y squared. So now let's find the first derivative. The derivative of 800y is just 800. And for negative 2y squared, it's negative 4y. And we'll set that equal to 0. Add in 4y to both sides, we get 800 is equal to 4y. And divide in both sides by 4, 800 divided by 4 is 200. So y is 200 feet. Now once we have the value for y, we can plug it into this equation to get x. So 800 minus 2 times 200, that's going to be equal to x. So that's 800 minus 400, which is 400 feet. So now we have the dimensions that's going to give us the maximum area. But the goal in this problem is to simply calculate that maximum area. So all we need to do at this point is multiply x by y. So x, this should be x, not y. X is 400 feet. And y is 200 feet. Now we know that 2 times 4 is 8, and then we'll add the 4 zeros. And so the total maximum area is going to be 80,000 square feet. Find a point on the line y equals 3x plus 5 that is closest to the origin. So let's draw a graph. Now, this linear equation, it's in slope-intercept form. So we can see that m, the number in front of x, is 3 and b is 5. So the y-intercept is 5 and the slope is 3. So I'm just going to draw a rough sketch. And let's say it looks something like that. We really don't need an exact picture. But somewhere along this line, we're going to have a point that is closest to the origin. So let's assume it's that point. Let's call it point P. If we draw a right triangle, we could say D is the distance between the origin, which is represented by O, and point P. And this is going to be x, which is going to be a negative value, and y is going to be a positive value. So notice that x squared plus y squared is equal to d squared. And so if we solve for d, d is going to be the square root of x squared plus y squared. So this is the objective function because we want to minimize the distance. And this equation here is the constraint. So let's replace y with 3x plus 5. So d is going to be the square root of x squared plus 3x plus 5 squared. Now we need to find the first derivative of that function. So I'm going to rewrite it first. So let's rewrite it as this expression. And let's raise it to the 1/2. Now, to differentiate that function, we need to use the chain rule. So let's start with the power rule. Let's move the 1/2 to the front, keep the inside function the same, and then we need to subtract the exponent by 1. 1/2 minus 1 is negative 1/2, and then we need to find the derivative of the inside function. The derivative of x squared is 2x, and to differentiate this, we need to use the chain rule again. So it's going to be plus 2, keep the inside part the same, 2 minus 1 is 1, times the derivative of the inside function, which is 3. So that's the first derivative. Now let's distribute the 1/2 to everything inside here. You shouldn't distribute it to both. It doesn't work that way. Just one of the brackets. So 1/2 times 2x is just x, and we can also cancel that too as well, because we have to distribute it to everything inside those brackets. So on top we're going to have, this is d prime by the way, x plus, I'm going to distribute 3 to 3x plus 5. So 3x times 3 is 9, and then 5 times 3 is 15. And on the bottom, if I move this to the bottom, the negative exponent will become positive 1/2, and then I can convert this back into a radical. So it's going to be the square root of x squared plus 3x plus 5 squared. Now we need to set this equal to 0. The good thing is, if the numerator is equal to 0, the entire fraction is equal to 0. So let's set the numerator equal to 0. X plus 9x is 10x. So 10x plus 15 is equal to 0. Moving the 15 to the other side, we have 10x is equal to negative 15. Divided by 10, that becomes 15 is 5 times 3. 10 is 5 times 2, so we could cancel 5. So x is negative 3 divided by 2, or negative 1.5. So this is the first answer. Now we need to find the y-coordinate of the point, which for the last step is not going to be too difficult to do. And so we have y. Y is 3x plus 5. So that's going to be 3 times negative 3 over 2 plus 5. So that's negative 9 over 2. And 5 we can multiply by 2 over 2. So it becomes 10 over 2. Negative 9 plus 10 is 1. So we have the point negative 3 over 2, comma 1/2. And so that is the point that is closest to the origin. And that's how you could find it. Number 10. Find a point on the line y equals 4 minus x that is closest to the point 7, 6. So let's begin by drawing a picture. So let's plot y equals 4 minus x. So the x-intercept, if we plug in 0 for x, y is going to be 4. So that's actually the y-intercept. To get the x-intercept, we need to plug in 0 for y and solve for x. So we get an x-intercept of 4. So we got the point 4 comma 0. And we also have the point 0, 4. So that's a rough sketch of the line y equals 4 minus x. Now at the point 7 comma 6, we need to find the point on the line y equals 4 minus x that is closest to this point. So how can we do that? Let's assume that point is here. So that point has an x value and it has a y value. Now let's draw a line connecting these 2 points. We want to minimize the distance between those 2 points. So once again, we could use the distance formula. D is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. So we could say that 7 is x2 and 6 is y2. And the point that we're looking for, we'll call this x1 and y1. So let's replace x2 with 7, and x1 we're going to replace it with x. y2 is equal to 6, and y1 we're just going to replace it with y. So we have this equation. Now just so you can understand what's happening here, this distance is x. This distance is 7. If we turn this into a right triangle, the base of that right triangle is the difference between 7 and x. So this base here is 7 minus x. Now this part is y, and this part here is 6. The difference between those two parts give us the height of the triangle, which is 6 minus y. And so the distance is basically the hypotenuse of that right triangle, which is basically the square root of a squared plus b squared. So now you see how this equation relates to the Pythagorean theorem of a right triangle. Now there's one more thing we need to do here before we could find the first derivative. Our goal is to minimize d. And right now, d is in terms of 2 variables, x and y. So what we need to do is we need to replace y with 4 minus x. So d is going to equal, now instead of writing this square root symbol, we can raise it to the 1/2. So this is going to be 7 minus x squared plus 6 minus, and then let's replace y with 4 minus x squared, and all of this is raised to the 1/2. Now 6 minus 4 is 2. Negative times negative x, that's going to be positive x. And so now at this point we have d in terms of one variable. We have d as the function of x. So now we could find the first derivative and set it equal to 0 to solve for x. So let's go ahead and do that. Let's use the power rule. Let's move the 1/2 to the front. We'll keep the inside the same. And then we're going to subtract the exponent by 1. So 1/2 minus 1 is -1/2. Next, based on the chain rule, we're going to take the derivative of the inside function. So the derivative of 7 minus x squared is going to be 2 times 7 minus x raised to the first power times the derivative of the inside, which is -1. For this part, it's going to be 2 times 2 plus x raised to the first power. We got to subtract this by 1. And then times the derivative of the inside. The derivative of 2 plus x is just 1. So this part here is going to be the numerator of the fraction that we're about to get. But let's distribute 1/2 to these two terms. This 1/2 will cancel with the 2's that we have here. So in the numerator, we have 2 plus x, and then we have a -7, and we have a positive x. Now this, we could bring it to the bottom, and it's going to be inside of a square root. So on the bottom, we have the square root of 7 minus x squared plus 2 plus x squared. And we're going to set this equal to 0. Now, because we have a fraction, if the numerator of the fraction is 0, the value of the entire fraction is 0. So technically, all we need to do is set the numerator to 0. So here we have x plus x, which is 2x. And then 2 minus 7, that's -5. That's going to be equal to 0. Add in 5 to both sides, we have 2x equals 5. Dividing both sides by 2, we have our x value, which is 5/2, or 2.5. So now that we have the value of x, we can calculate y. Y is 4 minus x. 4 minus 2.5 is 1.5. 1.5 is the same as 3/2. So thus we have the point P with the coordinates 5/2 and 3/2. So this is the point that is on the line y equals 4 minus x, but it's closest to the point 7, 6. So that's our answer. Number 11. Find the point on the curve y equals 6x squared minus x cubed plus 10 that has the highest slope, and calculate the maximum value of the slope. If we want to calculate the slope of the function, we need to find the derivative of the function. The derivative is a function that gives us the slope at some value of x. Our goal is to maximize the slope, so we need to maximize the derivative function. To maximize the derivative function, the second derivative must be set equal to 0. When the second derivative is equal to 0, the first derivative may be a maximum value, or it could be a minimum value. So that's the goal for this problem. We need to find the second derivative of the function and set it equal to 0, and then solve for x. So let's begin with the first derivative. The derivative of x squared is 2x. The derivative of x cubed is 3x squared. And for the constant 10, the derivative for that is 0. So this gives us 12x minus 3x squared. Now let's find the second derivative. The derivative of 12x is simply 12. The derivative of 3x squared is -6x. If we factor out a 6, we'll get 2 minus x. Now let's set that equal to 0. We can clearly see that x is equal to 2. Now let's make a number line. So 2 is the critical point for the first derivative. If we were to plug in 3 into this function, 2 minus 3 will give us a negative value. If we were to plug in 1, 2 minus 1 will give us a positive value. So to the left of 2, the function is rising. To the right of 2, the first derivative, not the original function, but the first derivative is decreasing. So thus the first derivative has a maximum at 2. If these signs were reversed, that means that it would have a minimum value at 2. Thus, the point on the curve with the highest slope occurs at an x value of 2. So now we need to find the y value of that point. So let's plug in x into the original equation. So we have y is equal to 6 times 2 squared minus 2 raised to the third power plus 10. 2 squared is 4 times 6. That gives us 24. 2 to the third is 8. And 24 minus 8 is 16. 16 plus 10 is 26. So the point for the first part of the problem occurs at an x value of 2 and a y value of 26. So that's the answer for part A for this problem. Now let's move on to part B. Calculate the maximum value of the slope. The value of the slope can be found from the derivative function, which is right here. So we're going to plug in an x value of 2 into this function. So it's going to be 12 times 2 minus 3 times 2 squared. 12 times 2 is 24. 2 squared is 4 times 3, that's 12. So we get a slope of 12. So that is the value of the slope when x is equal to 2. And we could check to see if that is indeed the maximum slope. So let's make a table. And let's rewrite our first derivative function, which was 12x minus 3x squared. If we were to plug in 0, the slope would be 0. If we were to plug in 4, this would be 12 times 4 minus 3 times 4 squared. That would be 0. If we were to plug in 3 into this equation, it's 12 times 3 minus 3 times 3 squared. That will be 9. If we were to plug in 1, it will be 12 minus 3, which is also 9. So we could see that the maximum slope occurs at an x value of 2. So that's it for part B. So part B is equal to 12. Part A, the answer is 2, 26. Number 12. A rectangle is inscribed in a semicircle with a radius of 10 centimeters. What are the dimensions of the rectangle that will maximize its area? And also calculate the maximum area. Well, let's draw a picture. So let's say this is the semicircle. Let's see if I can do a better drawing. And we have a rectangle inscribed inside of the semicircle. So here's the y-axis and this is the x-axis. Now the radius of the semicircle is 10. So that means this point here along the x-axis is 10. And this point along the y-axis is 10. Now let's call this part of the rectangle x, and let's call this part y. So drawing a rectangle like this, we can see that the length of the rectangle is x and x, so it's 2x, and the width of the rectangle is this portion, which is y. So the area of the rectangle is length times width. The length is 2x, the width is y. So the area is just 2x times y. Now what is y in terms of x? To answer that question, we need to know the equation of a circle. The equation of a circle is x squared plus y squared is equal to r squared. Solving for y squared, if we subtract both sides by x squared, we get that y squared is r squared minus x squared. And then if we were to take the square root of both sides, y is going to be plus or minus the square root of r squared minus x squared. So that's the equation for a full circle. Now we have two signs, positive and negative. For the upper half of the circle, it's positive root r squared minus x squared. For the bottom half of the circle, it's y equals negative r squared minus x squared. So since we're dealing with the upper half of the semicircle, or rather the upper half of the circle, which is a semicircle, we could say that y is just the positive square root of r squared minus x squared. And r is 10, so r squared is going to be 100. So we have y is equal to the square root of 100 minus x squared. So we can say that the area is going to be 2x times the square root of 100 minus x squared. The area function is the objective function. That's the function that we're trying to maximize. And right now, we have it in terms of one variable. So we can go ahead and find the first derivative and set it equal to 0. Now, we need to use the product rule since we basically have two things multiplied to each other. And if you recall, the derivative of f times g is f prime g plus f of g prime. So think of the 2x as f and the square root of 100 minus x squared as g. So let's go ahead and find the first derivative of the area function. So the derivative of 2x is simply 2, that's f prime. We're going to keep g the same, so that's the square root of 100 minus x squared. Next, we'll keep the first part of the function the same, 2x, and then we need to differentiate this. So keep in mind, this is 100 minus x squared raised to the 1/2. So this is going to be times 1/2. We'll keep the inside part the same. We'll subtract the exponent by 1. 1/2 minus 1 is negative 1/2. And then we need to differentiate the inside part of the function. The derivative of negative x squared will be negative 2x. Now let's take a minute to make some space. So I'm going to rewrite the area function here. It's L times W, which is 2x times y, which is 2x times the square root of 100 minus x squared. So now let's delete this. And so we have a prime is equal to 2 square root 100 minus x squared. Now we can cancel the 2 and the 1/2. And so we're left with x times negative 2x, which is going to be negative 2x squared. And this term, we can move it to the bottom, make this exponent positive, and convert it back into its radical form. So in the bottom, we're just going to have the square root of 100 minus x squared. Now this, we can put it over 1. What we need to do is we need to get common denominators so we can combine it into a single fraction. So I'm going to multiply this fraction by 100 minus x squared, top and bottom. So now we have a prime is 2. When we multiply these two, the square root will disappear, and we're just going to get 100 minus x squared. And then we have the other term. So at this point, we can write it as a single fraction. So we can say that a prime This is 2 times 100, which is 200. Here we have negative 2x squared plus another negative 2x squared. So that's going to be negative 4x squared all over the square root of 100 minus x squared. So we're going to set this equal to 0. If we multiply both sides of this equation by 100 minus x squared, these will cancel. On the right, we'll get 0 times the square root of 100 minus x squared, which is still 0. So the end result is that we'll have the numerator equal to 0. If we add 4x squared to both sides, we get 200 is equal to 4x squared. Dividing both sides by 4, we get 50 is equal to x squared. And then we could take the square root of both sides. The square root of 50, we can write that as the square root of 25 times the square root of 2. And the square root of 25 is 5. So now we know what the value of x is. So x is 5 square root 2. So now we can calculate y. We know that y is the square root of 100 minus x squared, which is what we have here. And we know that x squared is 50. If you square this, you'll get 50. So this is the square root of 100 minus 50, which is the square root of 50. And we know that's going to simplify to 5 square root 2. So in this problem, both x and y have the same value. Now, our goal in part A is to determine the dimensions of the rectangle that will maximize this area, which means we want to calculate the length and the width of the rectangle. So the length of the rectangle is 2x, and x is 5 root 2. So the length of the rectangle in this problem is going to be 10 square root 2. So that's the first part of the answer. The width of the rectangle is simply equal to y, and y is 5 square root 2. And the units are centimeters. So we can write the dimensions as 10 square root 2 by 5 square root 2, length times width. Now part B, calculate the maximum area. Now that we know the dimensions of the rectangle, we can calculate the maximum area that we can form when the rectangle is inscribed in a semicircle with a radius of 10 centimeters. So the area is simply going to be the length of the rectangle times its width. The length is 10 square root 2. The width is 5 square root 2. Now 10 times 5 is 50. And the square root of 2 times the square root of 2 is the square root of 4, which is 2. So it's 50 times 2, which is 100. For these types of problems, whenever you have a rectangle inscribed in a semicircle and you're given the radius, a quick way to find the maximum area of the rectangle that's inscribed in such a semicircle is you could use this formula. The maximum area is simply going to be r squared. So in this problem, r is 10. 10 squared is 100. So you get 100 square centimeters. So don't forget to pay attention to the units. So that's a quick and simple way to calculate the maximum area. It's always going to be r squared for this type of problem. So the units for the dimension will be the same as the unit for the radius, but the unit for area will be square units. So if this is inches, the area will be square inches. If this was feet, the area will be square feet.